Hi, I'm John Barron from Google Research, and this paper is called Zip-NeRF, Anti-Aliased Grid-Based Neural Radiance Fields. So this paper is building on NeRF. NeRF is a way to reconstruct a 3D model of a scene from 2D images. The central idea is that you combine ray tracing and volumetric rendering and optimize over a volumetric representation of a scene using gradient descent. That scene representation can be the weights of a neural network, or some sort of voxelization of 3D space, or some combination of those things. NeRF works by casting rays from a virtual camera out into the scene and sampling points along those rays. And the coordinates of these points are then featurized using positional encoding, and those features are fed to some sort of neural network that then predicts volumetric density and color. There's a follow-up to NeRF called MIP-NeRF, where instead of casting a ray and sampling points along that ray, you cast a cone and sample conical frustums along that cone. Then instead of encoding points along the ray, you featurize entire volumes along the cone by using an integrated positional encoding. This fixes NeRF's aliasing problems and significantly improves image quality. In parallel with this work on anti-aliased NeRFs, there's also been a lot of papers that have explored ways to use grid-based representations of the scene instead of an MLP. Here we have InstantNGP, which uses a hierarchy of 3D grids to model the scene, where a point in space is featurized by trilerping into its surrounding grid vertices and averaging and concatenating all of the learned codes that are stored in each vertex. This approach is nice because it significantly accelerates inference, but it doesn't do anything to fix NeRF's problems with aliasing. So zooming out a little, we see that we have NeRF here, which uses positional encoding and is both aliased and slow. Then we have MIP-NeRF, which uses integrated positional encoding and is anti-aliased but still slow. And we also have InstantNGP, which uses a multi-scale grid of learned features, and which is fast but also aliased. This paper is about filling in that missing box here, and we do this by using a combination of multisampling and downweighting. For multisampling, we need a way to turn a conical frustum into a small set of points that exactly match the mean and covariance of the conical frustum, just like in MIP-NeRF. I won't go into details, but there's a unique set of 6 points that does exactly this, which you can see here for 4 different conical frustums. We're going to treat these multisamples as the means of 6 isotropic Gaussians. Now, because these Gaussians are isotropic, there's a tidy analytical way to use their scales to downweigh high frequencies in the NGP hierarchy. We just weight each grid value by the fraction of the Gaussian that lies within each grid cell. So here we have a trained NeRF that uses an improved version of InstantNGP, and we can see that it exhibits a lot of what we call in the paper XY aliasing. That's spatial aliasing along the image plane, which is most noticeable in terms of the jaggies on the thin bike spokes here. And here's what we get by turning on this Zip-NeRF anti-aliasing. You can see that we're able to recover a lot of fine detail and that thin structures look nice and smooth. There's also another form of aliasing that our baseline model exhibited, which we'll call Z-aliasing. This is aliasing along the ray rather than along the image plane. Basically, sometimes samples along an array will arbitrarily miss or hit an object depending on the camera's distance to it, and this results in this strange tearing artifact as the camera moves in and out. And here we have a rendering from our model. I don't have time to get into details, but you can see that we're able to fix this Z-aliasing issue. Now let's look at some results. Here we have 2 ground truth image patches for 2 scenes in the dataset we'd like to use. And here we have InstantNGP's results, which trains quickly but produces blurry and oversmooth renderings. We also have MIP-NeRF 360's results, which was the most accurate algorithm on this benchmark at the time of submission, but which is very slow to train and also misses a lot of fine details. And here we have our algorithm, which trains about 24 times faster than MIP-NeRF 360 and produces significantly higher quality renderings than either baseline. Here's a video that was rendered from our model. This is a large scene that we captured ourselves to push the limits of what NeRF-like models can do, and you can see that Zip-NeRF is doing a great job. And that's it. Thanks. Here's another result from our model that I'll just let play for the rest of the video.